In this video, we're going to continue to analyze the concept of resonance. We've already looked at it and derived a couple of properties that are quite important. So here is our resonating harmonic oscillator driven by a sinusoidal force at long times longer than 1 over the damping time, the damping rate beta. With this definition, the transients have died out, and this is the form of the position versus time, where A is the amplitude, its squared is given by this formula here. Delta is the phase difference between the driving force and the motion of the oscillator, given by this formula here. If we plot A squared versus omega, we get this sharply peaked function around omega naught, and we found that the maximum of A squared is inversely proportional to beta squared, and the width of this peak is proportional to beta. So the peak gets larger and sharper the less damping we have. So now we're going to take a look at delta and see what its properties might be, this phase around resonance. So this is the phase, delta. So to analyze it, well, I'm going to rewrite it slightly here. This is arctangent, and I might as well write that also as an arc cotangent of omega naught squared minus omega squared divided by 2 beta omega. Then I'm going to use a result that you may not be familiar with, but through the magic of fast forward, I can derive really quickly over here on the right. So we get therefore and because arctangent is an odd function, we get that. Right. That's our result. If you don't remember what the arctangent looks like, I did plot it for you here. So you can see that for large values of x, it is asymptotically approaches pi over 2. For large negative values of x, it asymptotically approaches minus pi over 2. That's essentially what we have here, except that we have to add pi over 2 to this, and also shift it so that instead of this point here, the midpoint being at the origin, it's located at omega naught squared. So we're at omega naught, at omega equals omega naught. So that means then that actually the plot looks like this. So what we can see here is that if we are far below the resonance frequency, then delta is 0. If we are far above the resonance frequency, then delta is pi. And if we are at the resonance frequency, omega naught, basically if omega naught equals omega, then delta equals pi over 2. So to put that differently, so delta equals 0 means that the oscillator and the driving force move both in the same direction at the same time. If we are at the resonance frequency, well, then the phase difference between them is 90 degrees. Then instead of being in phase, we say that we are in quadrature. Essentially 90 degrees behind. The actual oscillator is 90 degrees behind the driving force. And if the frequency is well above the resonance frequency, then the oscillator is out of phase with the driving force. So before wrapping up this section on resonance, I have one other concept I need to introduce to you. And that is the concept of the quality factor, or usually just known as the Q factor. So the quality factor is just defined as the resonance position divided by the resonance width. So the resonance position is roughly omega 0, and the resonance width is just 2 beta. So that's the definition of the quality factor. So what it measures is how good of an oscillator you have, right? So the smaller beta, that is the less damping you have, the larger Q becomes. So it has a few different physical meanings. We can see, for instance, that we know that a period is 2 pi divided by omega, or omega naught. That's the natural period. And 1 over beta, that's the decay time of the damped oscillator. So with those definitions, that gives us that the Q factor will be pi times the decay time over the period. Right? So the Q factor tells you how long does it take for the oscillator to ring down. How many periods before the amplitude of the oscillator has gone down by a factor of E, the base of the natural logarithm. We will also show, and this will be on the homework, that we can also say that the Q factor, its physical interpretation, is that of the energy stored in the oscillator divided by the energy dissipated per period. Or per cycle. So that's the quality factor. So if we have a high Q factor, that means we have a slow ring down, we have a large amplitude on resonance, and we have large energy storage in oscillating mode. We haven't shown yet actually what the amplitude on resonance is in terms of Q factor, so let's do that. We have that A max squared is given by this, okay, and here's the definition of the Q factor right there. So that means that we can replace 4 beta squared with omega squared divided by Q, or divided by Q squared, of course. So this becomes equal to, so large Q factor means large amplitude, obviously. Okay, and the Q factor, like I said, can in some oscillators be very large. So just to give some examples here. So if you look at a tuning fork, which is an example of a resonator, it might have a Q on the order of 100 to 10,000. Typical LC circuit, maybe 1,000 to 10,000. If you look at a quartz crystal, just like the quartz crystals that are used in computers to keep time, to run the clock inside the computer, or to keep track of time in your watches, that has a Q on the order of 10,000 to 1,000,000 perhaps. Largest ever recorded. That would be in a single crystal at low temperature that people isolated as well as they possibly could from the environment. Now they actually measured Q factors of 10 to the 11. So that means that that oscillator rings 100 billion times before its amplitude is reduced by a factor of E. So let's go back to the beginning of this video and summarize what we have learned. So we know that this is what the amplitude squared looks like. Here's the phase. Plotted the same way. And let's now summarize what we found out about the phase. And we define the Q factor. That means we can rewrite both the maximum amplitude and the full width of half maximum accordingly. So one thing we haven't discussed yet is actually why resonance is important. It is something that is rather ubiquitous in physics. You'll find it in a huge number of instances. So some examples of resonators that you may encounter include the voice box, the part of your anatomy that allows you to speak. And in fact, the voice box connected to all sorts of cavities within your head. They are all resonators, and their characters of those resonators give your voice the sound that it has. The same thing really for musical instruments. And we already mentioned quartz crystals. That is the quartz crystals that are used in watches and computers. Another case of resonators which are less desirable are buildings. You want to generally avoid to have resonators in buildings, resonances in buildings that coincide with something that might excite them, and that's something that architects need to take into account in order to avoid catastrophic failure in a storm or something like that. Atoms can be seen as a case of a resonator. If light interacts with an atom, takes an electron, moves it from the ground state to an excited state, that's something you will study in quantum mechanics, that's really a case of resonance. It can be treated with pretty much the same formalism. And on a larger scale, lasers are a form of resonators. So resonance is a crucial concept that you need to understand in detail, and that's why I've taken the trouble to derive all these properties that it has. Now, when you look at an actual mechanical system, generally it doesn't have just one resonance. It has multiple resonances. And in fact, what gives a musical instrument the particular sound that it has is the set of resonances that it possesses, at least in part. The other factor that gives a musical instrument the sound that it has is the driving force. We've assumed here that the driving force is sinusoidal and has a single frequency. In general, that's not at all necessary to make that assumption. As long as you stick with a periodic function, it is in fact quite within our powers to analyze the situation of a non-sinusoidal driving force. And that's what we're going to do in the next video. This will require a little bit of Fourier analysis, but other than that, it works pretty much exactly in the same way as this analysis.